The new section is entitled Jointly Distributed Random Variables. Let's write that down. Jointly distributive random variables. Now we're going to have two random variables. Okay, so let's state that. Suppose we now have two random variables, x and y. And now we want to define what we mean by a joint cumulative probability distribution function. A lot of words. Joint cumulative probability distribution function. Of x and y. Of the random variables x and y. And the definition is, we call it f of a comma b. This is the probability that the random variable x is less than or equal to a, and the random variable y is less than b, less than or equal to b. So chances x is less than a, and at the same time y is less than b. And it turns out, of course, that a and b are somewhere between negative infinity and positive infinity. But of course they can't equal either infinities, sorry. Okay, basically, a and b are real numbers. Okay, now, we like to know just the distribution of just x. And we want to get it from the jointly distributive random variable. That is the joint cumulative probability distribution function. Okay. So basically, you let b go to infinity. Let's see how we describe this. We call it fx of a. F, random variable x of a. This is equal to the probability that just x is less than a. Okay, but you might ask, well, what happened to y? Well, y can be any value. X is less than a, and y is less than infinity. Y can be any value. Okay, just let y go to infinity. Oh, sorry. Let the letter b go to infinity. Y can be any number less than infinity. It can be negative 98. It can be the square root of pi. It can be pi cubed over 11. It can be any number. So from the joint cumulative probability distribution function of x and y, we can find just the distribution function of x. It's pretty neat. Just say y is less than infinity. Now, well, we probably won't ever write this again, but that's what it means. That is, when we have f sub x of a, it means the probability that x is less than a and y is less than infinity. And of course, I can define f sub y of b, and this is going to be the probability that y is less than b. That means x can be anything. And since a can be anything. And since A goes from negative infinity to infinity, well, it can be anything, like I just said. That is, x is less than infinity. It's certainly not equal to it, sorry. X is less than infinity. And the random variable y is less than or equal to the number b, the real number b. Okay. Sometimes some folks would call these two functions the marginal distribution function. Marginal. Okay, so just some notation here. Now, let me write down one thing that we just talked about, or defined, so it's in front of us, and then we'll talk about something else. Of course, we'll use this something. All right, so we know that by definition that, let's see what I want to say. Well, f of AB, let's see something. Yeah, f of AB is the probability that x is less than A and y is less than B. Okay? So the question is, what is the probability that x is bigger than A and y is bigger than B? Okay, well, remember, if you add the complement, of x is bigger than A and y is bigger than B, if you add on the complement, you get 1. Okay, I'm going to bring this over to the other side. So the probability that x is bigger than A and y is bigger than B is 1 minus the probability of x is bigger than A and y is bigger than B, complement. I chose my words carefully when I first defined the top line. I said this is the probability that x is less than or equal to A and y is less than or equal to B. That is, there's an and here. We have one set intersect another set. Remember, if you have the intersection of two sets, you take the complement. Even if that was union, what I'm about to say is true. We change 4 things. It's easy, everything we see. 1, 2, 3, and 4. A becomes a complement. If it's intersection, we put union. If it were union, where number 2 is, I would put intersection here. B becomes B complement. And if there's no complement here, then I put a complement there. If there is a complement by number 4, then I don't put a complement right there. And that's what we're going to use right now. So this is equal to 1 minus the probability. The complement of this is x's are less than or equal to A. The intersection becomes union, and y greater than B, if that's not true, then y must be less than or equal to B. Okay, so we have that. Let me erase this and put down another formula that we learned earlier on. Probability of A union B. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Oops, the first part didn't come. The probability of A union B is equal to that. I have probability of what's in these big brackets. I'm thinking of that as A, and that is B, that A and that B, and the union. So I have 1 minus, it's the probability of A, which is X is less than or equal to A, plus the probability of B. I'm calling that B. That means Y is less than or equal to B. The random variable Y, which is capital B, minus the probability of their intersection. The probability that X is less than A and Y is less than B. Okay. So we have 1, and we have to take away this. But that's just fx of A. And we have to take away this term minus, that's fy of B. And we have to take away the last term, but if you take away a negative, it becomes positive. And by definition, look at the very, very top. The probability that X is less than A and Y is less than B, and that should be little b. Well, that's just f of AB. And we, using the definition, we derived the formula for the probability that X is less than A and, X is bigger than A and Y is bigger than B. Here it is right here. Okay. Now, let's do another one. This is a fun one that we're going to do, I think. What if X is not just less than A, but it's between A and B, say? Not just X is less than A, meaning from negative infinity to A. What if X is between two values? The same for Y. What is the probability that X is between A1 and A2, and likewise, Y is in between B1 and B2? What should that equal? Okay. Well, let's put this on for two-dimensional setting. X goes from A1 to A2, random variable X and random variable Y. And Y goes from B1 to B2. So that's A1, this is A2, B1, and B2. We want the probability of being in here. Okay, we want the probability of being in here. Why? Because every point in that rectangle has a property that X is between A1 and A2, and Y is between B1 and B2. Just the way it is. And no other point has that property. This point, it clearly has that Y is between B1 and B2. But the X value is, it's less than A1. It's not between A1 and A2. Okay, let me erase this in the middle. So somehow, we want to just find the area inside there. Probability is area. Okay, so let's just use something that will get at least that area. It might get more, but at least it'll have the area. F of A2, B2. That is the probability that X is less than A2 and Y is less than B2. Well, That's all of this area. Let's forget about when it's negative. In reality, it really goes down forever. Okay. So, what I wrote down did capture the area that we wanted. The only problem is it got too much. So, you have too much, you take away. I'm going to take away f of a1, b2. That is, x is less than a1 and y is less than b2. That's this area over here. Okay, that's this area over here. So, I took it away. I took it away. I'll keep that line, the dotted line. Alright, now, I really like to take away this area here. How about we call that f of a2b1? That is, I'll take away the points where x's are less than or a2 or equal to, and y is less than b1. Y is less than or equal to b1. Okay, we'll put some dots here. The area that I just took away is all of this area. All of this area. And you say, wow, we're doing good, we're doing good. We're only left with the area we wanted. But there's one problem. This area here, we took it away twice. And you just can't take it away twice. In fact, a moment ago it was empty. And we just took it away. So, we can't do that, so we have to put it back. We have to put it back. That is, we have to add f of a1b1. Okay, so let me just remove this for one moment, or let me remove it for many moments, and say, there's our formula, including the bottom piece. That's the formula for the top. And all we did was we found some probability that contained this area, but unfortunately it contained too much. In fact, it contained region 1, 2, and 3. In fact, how about we number them? How about we number them? 1, 2, 3, and 4. So, this first probability, f of a2b2, contained 1, 2, 3, and 4. And then we took away f of a1, b2. a1, b2 with this area here. So we took away 1 and we took away 2. And then we took away a2b1. We took away a2b1. a2b1. Let's see what area that is. a2b1. That's this area down here. That is, we take away 2 and 3. Well, we can take away 2 again. I mean, we did. And we took away 3. But we didn't have 2 to take away. So, I have to add 2 back. And all I'm left with is 4. Okay, we're just left with region 4, which is exactly what I wanted. Maybe I shouldn't have used the cross-out method. F of A1, A2 is 1 plus 2 plus 3 plus 4. Minus f of a1, b2 was minus 1 and minus 2. And f of a2, b1 is 2 and 3 we have to take away. Okay, so now we're not going to say 1 plus 2 is 3. Now these are names of regions. 1 and then we took it away. 2 and then we took it away. 3 and then we took it away. Now I want the answer to be 4. Region 4, but I have 4 minus 2. Oh, I'll add 2 back. And that's what I did right there. And I came up with just region 4. So that worked out nicely. Okay. All right, so now, what if x and y are discrete random variables? X and y are discrete random variables, meaning that they're not continuous. X can maybe be just 1, 2, 3, and 4. Like if you shoot a basketball 10 times, how many times might it go in to the loop? And the answer cannot be 2 3/4 or pi times. Oh, you know, I shot the ball 10 times and went in pi times. Makes no sense. Or it went in 3 3/4 times. Makes no sense. Okay. Well, then the joint probability mass function of x and y, well, they are rho of xy is rho of x equal x and random variable y equals y. The probability mass function of x, which is denoted this way, that is, the probability that random variable x is x, well, this is the summation of y, such that, or I guess p of xy should be non-negative, of rho of xy. Little x, the random variable x, which we're saying is little x, doesn't change. Only y changes. Only y changes. And likewise, py of x, probability that y is little y, is going to be the summation as our over all x's, such that the probabilities are positive. Okay. So let's actually look at a numerical example. Let's see what's going on here. Suppose you have an urn, and the urn has 3 red and 4 white and 5 blue. There's a record that's 12. And you want to pick 3. You want to pick 3. And we're going to say, let the random variable x be the number of white balls drawn from the 3, and y equals the number, well, let's call this red. And the number of white balls will be y. Okay. So X is the number of red balls, and Y is the number of white balls. So find the probability mass function of X and Y. Well, what can they be? You're drawing 3 balls. Well, it's possible that the number of red is 0 and the number of white is 0. Or the number of red is 0 and you get 1 white. Or number of red is 0 and you get 2 red. I meant to say 2. 0 white, 0 reds, and 2 whites. Or maybe you get no reds, but you get 3 whites. And notice there are at least 3 whites. Well, what about 0 red and 4 whites? I mean, after all, there are 4 whites, but there's a problem there. And that problem is you've already picked 4 balls. There's no room to pick 4 balls. You're only picking 3. Okay, so this one is no longer there. So I wrote down all the cases where the number of reds are 1. And I do want to move this over a little bit. I need the space. Okay, so we had 0, 1. 0, 3, excuse me. Well, now what if you get 1 red? You can get no whites, or 1 red and 1 white, or 1 red and 2 whites. That's 3 balls. So you couldn't get 1 red and 3 whites. That'd be 4 balls. Likewise, you can't get 1 red and 4 whites. Okay, well, what if you get 2 whites, 2 reds? You can get no whites. Okay. Or you can get 1 white ball. Total is 3. Now, okay, so this is, in my opinion, I would call this a hypergeometric problem. From the 3 reds, we're going to choose some. From the 4 whites, we're going to choose some. And from the 5 blues, we're going to choose from. Now, we're choosing a total of 3 balls. We're not picking any red. We're not picking any whites. So far, we picked no balls. So we have to pick 3 from the red. From the blue. And from the 12 balls in total, we are going to pick 3. Let's do this one. From the 3 reds, we're going to pick some. From the 4 whites. From the 5 blues. We are going to pick no red, 1 white. So far we picked 1. So we have to pick 2 to be blue. And this gets divided by 12, choose 3. We're going to pick some of the 3 red balls. We're going to pick some of the 4 whites. And that sum might be 0. And we're going to pick 5. We're going to pick some from the 5 blues. In fact, we're going to pick 0 whites and, we're going to pick 0 reds and 2 whites. And that's 2 balls, so the third one must be blue. And this is 12, choose 3. This one, we're going to pick some from the red, some from the 4 whites, some from the 5 blues. 0 reds, 3 whites. We already picked 3 balls, so we don't have to pick any from the blues. And this is over 12, choose 3. 1, 0. From the 3 reds, we're going to pick 1. From the 4 whites, we're going to pick none. And from the 5 blues, we're going to pick 2. So far, after red and white, we only picked 2. 1, 1, 1. 1 plus 0 is 1. Have to add 2 more. And this, like always, gets divided by 12, choose 3. This one's going to be, well, from the 3 reds, we pick 1. From the 4 whites, we also pick 1. And then from the 5 blues, 1 plus 1 is 2. We pick 1 more. 3. And this gets divided by 12, choose 3. And here, from the 3 reds, we pick 1. From the 4 whites, we pick 2. We've already picked 3 balls. So from the 5 blues, we take none. And this gets divided by 12, choose 3. There's a reason I want all of these on the board, so let's put it up. There's a couple of more. Two, 1, 2, 0, 2, 0, and 2, 1. Okay. So from this 3, we want to pick 2 of them. From the 4, we want to choose 0. And from the 5, I've already chosen 2 and 0, which is 2. We want to choose 1 more for a total of 3. And it's divided by 12. 12, choose 3. 2, 1. From the 3 reds, I want to choose 2. From the 4 whites, I want to choose 1. And from the 5 blues, I've already chosen 3, so I can't choose any more. We're choosing 3 balls. That was the premise. And this gets divided by 12, choose 3. Now, the probabilities are, if you calculate this, which I did, it's 10 over 220. It's 40 over 220. 0.2 is 30 over 220. 0.3 is 4 over 220. 10 is 40 over 220. Actually, it's 30 over 220. 1 is 60 over 220. 2 is 18 over 220. 20 is 15 over 220. And 21, oh, there's a little error there, but no big deal. 21 is 12 over 220. And there's no reason why we can't have 3 reds and no whites. So from the 3 reds, we want to choose all 3. From the 4 whites, we want to choose 0. I've already chosen 3, so I can't choose any from the 5. And this gets divided by 12, choose 3. And this number happens to be just 1 out of 220. Okay, so we have all of this. And unfortunately, I can't have everything on this board and then make this table. Okay, maybe you want to write down these numbers so they're in front of you. Nonetheless, we're going to make up a table. There's a reason why we want this table. And the reason we want the table is because it gives us the PMF. Okay. Okay, so we have this table, and for x, it could have only been 0, 1, 2, and 3, and for the y's, it can only be 0, 1, 2, or 3, because you only pick 2 balls. So we have i's and we have j's. I's are these numbers, and the j's are those numbers. And remember the probability. Let's see how we did this. The probability of ij. Red and white. Okay. So in here, the number that goes in there is the probability that you get 0 reds and 0 whites. And that probability was 10 over 220. The number, for example, that you put there. Well, just look to the left. You get 1 red and 2 white. The probability that you got 1 red and 2 whites, keep in mind we calculated all of these. 1 red and 2 white is 18 over 220. And I'm just going to fill in the table for us. 40 over 220, 30 over 220, 4 over 220, etc. Why are the rest 0? I'll even erase this one. The reason is, for example, the number that goes in there, it will have 1 red and 3 whites. But that's impossible. That's 4 balls already. The number that goes in here, just look to the left. It'll have 2 reds and look up. It'll have 2 whites. It's already 4 balls. 2 red and 3 whites, forget about it. If you're going to have 3 reds, then the best you can do, the only thing you can do is have 0 whites. You can't have 1 white, or 2 whites, or 3 whites. That is the probability that that happens is absolutely 0. Now, down here, we have the probability that y equals j. And I want to get rid of this here because I need the space. And I'm going to add up the rows and the columns. When I add up this column, I get 40, 55, get 56 over 220. The next column, 112 over 220. The next column is 48 over 220. And then 4 over 220. Now I'm going to add up the rows. The first row adds up to 84 over 220. The next one, the 108 over 220. The next one looks like 27 over 220, and the last one is 1 over 220. I just added up all these numbers, and I got 27 over 220. And the heading is the probability that x takes on the value I. That is, what does this number mean? Well, the probability that x is equal to I. This is really px of x equal I. We just go to the left and you find out what I is. 108 over 220 is the probability that x takes on the number, just look to the left, 1. Notice y could have been anything. Like for this one here, the probability that x is 2. Well, first I take the probability that x is 2 and y is 0. Look above, you find out that y is 0. Plus 12 over 220. That's the probability that x is 2 and y is 1. Plus the probability that x is 2 and y is 2. Plus the probability that x is 2 and y is 3. The probability that x is 1, y is 0. Plus this number. The probability that x is 1, y is 1. X is always 1, but we let y be any value that y can be. And we add them up. We add them up. This is known as the probability that x takes on the number 1. Called the PMF. And likewise, this number right here is the probability that y takes on the number 0. I look straight above. This is the probability that y equals 1. That number is the probability that y equals 2. And this last number, the probability that y is equal to 3. Add the columns, you find the PYs. That's important. Okay. At some point we'll make up a table for this one. So, in some town, 15% of families have 0 children. And 20% have 1 child. And 35% have 2 children. And 30% have 3. Nobody has more than 3, and it's discrete. That is, you can't have 1.8 kids. It just doesn't make sense. What does 0.8 of a child look like? You can't have pi children. You can give children pie to eat, but you can't have pi of them. We'll also assume that the chance of having a boy or a girl are equal. A half. Why? Because you can only have a boy or a girl. Whether they add up to, whether they're equal or not, the probability of having a boy plus the probability that you have a girl, the chances that you have a boy plus the chance that you have a girl must be 100%. 100% of the times you're going to have a boy or a girl. 100% is 1. Okay, since I'm telling you that these two quantities are equal, they can't be a third, because when you add a third to a third, you get 2/3. It's not 1. It can be a quarter. You have two numbers that are the same that add up to 1. Those numbers are half. What number, when you add it to itself, gives you 1? I call it unknown x. What number, when you add it to itself, gives you 1? X plus x is 2, x is 1. Divide both sides by 2, and you find out that x is a half. Okay. In any case, we're going to assume that the chances of having a boy or a girl are identical. So they both equal a half. Okay. So you pick a family at random, and basically you want to fill in this table. Boys, girls. Well, when you pick a family, they can either have 1, 2, or 3 girls, 0, 1, 2, or 3. You have pick a family. The number of boys can be 0, 1, 2, or 3. But remember, nobody has more than 3 children. Nobody has more than 3 children. So the instructions are to fill in this table. What I'll do here is, for right now, I'll find the ones whose probabilities are 0. If you have 0 girls, you could have 0 boys, which means no children. Or you can have 1 boy, which means 1 child, because you have 0 girls. And 0 girls and 2 boys is 2, which is okay. And 0 boys and 3 girls are okay, because that's a total of 3. But if you have 1 girl, you can't have 3 boys, because that would mean you have 4 children. If you have 2 girls, you can have 2 boys, which is right above, and also you can have 3 girls, which is right above. That is, those chances are 0. If you have 3 girls, yes, you can have then you have to have no boys. You can't have 1 boy, because then you would have 4 children. You can't have 2 boys. You can't have 3 boys. By the way, these numbers add up to 100%. That means there are no other cases. You either have 0 kids or 1, 2, or 3 kids. Okay. So, on the side, I'm going to figure out these 4, 5, 6, 7, 8, 9 probabilities. But I need the space here. And as you find those numbers, you fill them in the table. Now, I do want to say one thing. I should have made this comment. 0, 1, 2, 3. 0, 1, 2, 3. Since the chances on having a boy and a girl are exactly the same, let's just suppose for a moment this probability was 0.8. Oops. 0, 1, 2, 3. 2, 1, 0. Let's suppose that, and this is 0.7, and this is 0.2, and this is 0.4, and this is 0, and this is 0.3, and you have 0 and 0, and you have 0, 0, and 0. and this is 0.86. Suppose you had those numbers. You don't even need to mention these. This picture should be symmetric because the chances that you have, two, well, I don't know if I wrote this yet, but let's say boys and then girls. Actually, I've been saying the opposite, haven't I? Which is fine. Boys and girls. The chances that you have two boys, two girls, and one boy, that's going to be the same as you having one girl and two boys. The probability that you have three girls and no boys should be the same as you having no boys and three girls. It's symmetrical. That is, everything on this diagonal should be symmetrical. That is, if you have 0.7 first up there, then you should have 0.7 down here, and 0.8 in the middle. Let's look at this diagonal here. First you have 0.8, so last you should have 0.8. Then you have 0.3, so going in this direction, you should have 0.3 next. In this diagonal, if that's 0.2, well then that's 0.2. And if this one's 0, that's 0. And if this is 0, then that should be 0. Because no matter which way you read the diagonal, it should be the same. If one student reads this diagonal from bottom left to the top right, they'll say 0.7, 0.8, 0.7. If another student read from the top right down to the bottom left, they'll say the same three numbers, 0.8, 0.7, 0.8, then 0.7. It's symmetrical. So that should help us a little bit in filling in this table. We only have to find a little bit more than half. Okay. So what are the chances that, just for me, it's girls and then boys. What are the chances that you have 0 girls and 0 boys? Well, this is a probability that you have no children. And of all the probabilities that we're going to compute right now, that's the easiest one. Outright the easiest one. The others are going to be a little bit more of a pain. This answer is 0.15 because the probability that you have no children is 15%. It's 0.15. Probability that you have 0 girls and 0 boys. Okay, what's the probability that you have 0 boys, 0 girls, and 1 boy? By the way, that's going to be the same as having 1 girl and no boys. But let's compute this one. So we want the probability that you have 1 child and it's a girl. Probability that you have 1 child and it's a girl. Okay. Now, remember, the probability of A given B is equal to the probability of A and B divided by the probability of the second one, which is B. Cross multiplying, this comes up here. Okay? That is, whenever you have the probability of A and B, you can write it down as a conditional probability. Now, unions are, intersections as well as unions actually, commute. That is, this is the same as A intersect B is the same as B intersect A. That is, I want to call that A and that B. Okay. So, this is nothing more than the probability of B intersect A, or the probability of A intersect B. But I know what that is. It's this here. It's the probability of A, that is having a girl, given that B, you have one child, times the probability of B, the probability that you have one child. Probability that you have one child. Okay. Given that you have one kid, given that you have one child, what's the probability that it's a girl? Answer the half. Times, so that's what this equals, times the probability of having one child, 20%, 0.2. This is 1/10, if I'm not mistaken. Okay, so the probability that you have 0 girls and 1 boy is 1/10, which is the same as the probability that you have 1 girl and 1 boy. So for free, just writing this down gave me 2 answers. I just computed this one, and I got 1/10, but now I know that one. It's symmetrical. You can switch the boys and the girls. Okay. If having boys and girls are equal, there's no reason to assume that when you see a family of 5 kids, it's more likely that they'll have 4 boys and 1 girl. It's no more likely that they'll have 4 boys and 1 girl than 4 girls and 1 boy. It's symmetrical. You're not going to have 2 neighbors who have 5 kids. One has 4 boys and 1 girl, and you're like, okay, 4 boys, 1 girl. But another family has 4 girls and 1 boy, and you say, wow, that's unusual. It's no more unusual as the other way. Let's do one more. At least one more. So, I think it was girls, boys. What are the chances that you have 0 girls and 2 boys? Well, this is the probability that you have 2 children and both girls. Sorry, and both are boys. Well, this is just the same as the probability of 2 boys and 2 children. If I call this A and that B, this is the probability of A and B, which is the same as the probability of A given B times the probability of B. Why do we want to do this? Because I don't know this answer. But I know the first. I can calculate the first probability, and I can calculate the second probability. The probability that you have 2 boys given that you have 2 children times the probability that you have 2 kids. Okay, so let's work on the first probability. We know you have exactly 2 children. What are the chances that they're boys? Well, you can have a boy and then another boy. You can have a boy and then a girl. Or you can have a girl and then a boy. Or a girl and then another girl. 1 out of 4 have 2 boys. So it's 1 out of 4 times the probability that you have 2 kids is 0.35. So you have 0.35 over 4. Move the decimal 2 places on top. Get 35. Move it on the bottom. And 5 goes into both of these numbers 7 times. And 80 times. Okay. So 7 out of 80 times, you will have 0 girls and 2 boys in this neighborhood. Okay. Let's try another one. What if you have 1 girl? Oh, and this last one that I just erased, it was the probability that you have no girls and 2 boys. This was the same as you having 2 girls and no boys. It's the same 7 out of 80. So you can fill in both of those entries on that table. So I don't have the table in front of me, but right now I'm calculating the probabilities so I can fill in the table. Just because I have a bad memory, I'm going to write girls and then boys. Okay, what is the probability you have 1 girl and 2 boys? So this is equal to the probability that you have 1 girl. Let's write this down nicely. One girl, 1 boy, and 3 children. But this is just the same as having or writing. Actually. Okay. So, this is my A intercept, and this is my B. This is the probability of A and B. And here it is. You have to know, if you can't calculate that exactly, you can go to the probability of A given B times the probability of B. For the record, this is the same as the probability of B given A times the probability of. It's always the one that comes after the given that you put inside here. Those two should match. These two should match, and they do. Okay, but we're going to use the first one. This is the probability of having 1 girl and 2 boys, 1 girl and 2 boys, given that you have 3 children, times the probability that you have 3 children. Well, the probability you have 3 children, we know, is 0.3. 0.3 times, so we know you have 3 children. What's the chances you have 1 girl and 2 boys? By the way, before I forget, this is the same as having 2 girls and 1 boy. Okay. Well, you have 3 kids. You can write down the sample space if you like. You can have a boy. Now, boy first for a while. A boy, and then a boy and another boy. The second child can be a boy, and then the third a girl. So the second can be a girl, and then a boy. And then a girl, and then another girl. But the first ones, will all be boys. Or the first kid can be a girl. And now let's list what the second and third can be. It can be a boy and then a boy, or a boy and then a girl. You have a girl second and then a boy, or a girl and a girl. How many of these have one girl and two boys? Well, this has one girl and two boys. This has one girl and two boys. And this has one girl and two boys. It's 3 out of 8. It's 3 out of 8. Point 3 is 3 out of 10. 3 times 3 over 8 times 10. 9 out of 80 times you will have 2 girls and a boy, or 1 girl and 2 boys. And the rest are the same. Just crank them out. Write down the sample space. We talked about sample spaces a long time ago in this video. Go back and look at it. You can always rewind. Okay, so up to now we've been talking about 2 random variables and what we can do with them, but the random variables have been discrete. What if they are continuous? Suppose x and y are jointly continuous random variables. If that's the case, then the probability that x at the point xy is contained in some set C is going to be a double integral of f of xy dx dy over C. That is, xy must live in C. This here is called the joint density function of x and y. This is a double integral. So, for example, what would f of AB equal? Now, remember, this is the probability that x is less than A and y is less than B. Okay? So, this is going to, so what that means is that x is in negative infinity A and y is in negative infinity B. So, just like the C. Okay. C is in R2. Okay. So now using our formula, this is going to be the double integral. In this formula right here, will be the double integral of f of xy dx dy. Of course, you can interchange those. You can write dy first, but if you write dx first, then that's going to be the x limits, and x goes from negative infinity up to A, and y goes from negative infinity up to B. Remember, the first integral you work on is the inner one. First, you calculate that integral. And since that's x's, then your limits on the integral here should be x values. And then whatever you get, whatever this happens to be, you integrate with respect to y. So these should be the y limit. And they are. And they are. Now, what if we take, so I'm going to write this a little bit smaller. Now, what if we take the derivative like 2 times? So this is equal to the integral from negative infinity to b of the integral from negative infinity to a f of xy dx dy. Okay. Now, when you do this first integral, it's going to be and whatever you get, maybe the antiderivative of this is, I don't know, x squared y. And then you go from 0 to a. So you're going to get a squared y. And now you integrate this with respect to y. You integrate with respect to y. And you get a squared y squared over 2. And it goes, say it goes from 0 to b. So you get a squared b squared over 2. That is, you get a function of a and b. You get a function of a and b. So we need to keep that in mind when we integrate. Or, sorry, if we take the derivative. If I take the partial of this, if I take the partial of f of ab with respect to, say, a, and then with respect to b, if I do the same thing over here, if I do this actually first with respect to b and then with respect to a, what I'm going to get is just the double derivative on the right side is just going to be f of ab. So that's the connection between big F. That's another connection between big F and little a. I say another. What's even one more? Well, I just said one. Big F of AB is the double integral of f of xy dx dy. But another thing is the partial of big F with respect to little a with respect to little b is little f of AB. Okay. So let's try to do a couple of problems. Suppose the joint density function of x and y is given by this formula. The joint density function of x and y is given by f of xy is piecewise. Sometimes it's e to the negative x times e to the negative 2y. Other times it's 0. So you might ask, oh my, when is it 2e to the negative x times e to the negative 2y? Answer is when both x and y are between 0 and infinity. When is it 0? Otherwise. If x and y are not both between 0 and infinity, they can both be negative, or one can be positive and the other one can be negative. Or one can be positive and one can be 0. And we want to make some computations. The first one is, what's the probability that x is bigger than 1 and y is less than 1? Okay. Well, this is going to be the double integral. And first I'll write dx. And x's go from 1 to infinity. And y is less than 1. So, y is less than 1. Remember, y is between 0 and infinity. So if it's less than 1, it's from 0 to 1. And we put f of xy there. But what is f of xy in our intervals? Well, if x goes from 1 to infinity, it's in here. And if y goes from 0 to 1, it's in here. So that is the formula I use for f of xy. 2e to the negative x, e to the negative 2y, dx, dy. Okay, I think we should rewrite this. The 2 can come all the way in front. And then anything that has y's, like this piece, that factor, and that factor, they can come in front, times the integral of e to the negative x times dx. And x goes from 1 to infinity, 0 to 1. So it's 2 times the integral of e to the negative. I don't feel comfortable with one thing. It's not wrong, I just don't feel comfortable. Actually, maybe it is wrong. The dy, I want to put that on the end. dy. So it's 2, the integral of e to the negative 2y. Now, let me work on this integral right here. Obviously, I'm going to need some more space. Okay. Now, you're required to know your integral forms. The integral of e to the kx dx. Now, to be honest, sometimes I forget this formula, but I know one thing. E to the kx is going to be part of the answer. And when I take the derivative of this, I'm supposed to get that back. But the derivative of e to any power is e to the power times the derivative of the power. The derivative of a number times x is just a number. Oh, I don't want k, I just wanted this. Oh, I'll divide by k. You divide by the derivative of the power. Okay, so now if k is negative 1, I get e to the negative 1x divided by negative 1. That is, I get 1 over e to the x. A positive divided by a negative is a negative. Dividing by 1, don't bother doing. Dividing by 1 won't do anything. So you just left with e to the negative x. You put the e to the negative x on the bottom as e to the plus x. You have to put something on the top. Put a 1. And the sign was negative. And we're going from 1 to infinity. I hate this being negative. I'm going to change the sign, but then I have to swap the limits. Infinity to 1. You plug 1 in here, e to the 1 is e. You get 1 over e, minus. You plug in a really, really large number. E to that large number is large. And 1 divided by really, really large is 0. So you just get 1 over e. So this integral is just 1 over e. And you can factor that out in front. Okay. So let's do this integral down here. 2 over e is a constant. I do want to do one thing. The limits are 0 to 1. The integral of e to the negative 2y is e to the negative 2y divided by the derivative, which is negative 2. And we are going from 0 to 1. That's negative 1 over e. Negative 1 over e times e to the negative 2y. From 0 to 1. Since it's negative, I'm going to write it positive. Positive 1 over e. But this has a negative exponent. I'll put it in the bottom. E to the 2y. Since I changed the sign, I have to switch the order of the limits. You plug 0 in. 2 times 0 is 0. E to the 0 is 1. E times 1 is e. So you get 1 over e. Minus, now you plug 1 in. 2 times 1 is 2, so you get e squared times another e. So you have e cubed on the bottom with the 1 on the top. Okay. And if you like, you can factor out a 1 over e. 1 over e times 1 gives me 1 over e. 1 over e times, or 1 times 1 gives me the 1. E times e squared gives me e cubed. Either one of those is acceptable. Okay. So let's do another one. Same PMF. Actually, it's continuous, so it's a joint density function. Again, f of xy is 2e to the negative x, or e to the negative 2y, 0, when x and y are both less than infinity. And you get 0 otherwise, elsewhere. Okay. So now, the question is, what is the probability that x is less than y? What is the probability that x is less than y? Well, it's going to be the double integral of the PDF, e to the negative 2y, dx, dy, and it's going to be over xy's, where x is less than y. The set of xy's such that x is less than y. Okay. And of course, x and y's are not negative. X and y are between 0 and 2. Okay. So let's see how we are going to put the limits down. Dx, dy. The first limit, first integral, is limit goes where y is. And y's go from 0 to infinity. Now the second one says x is less than y. X is less than y. Well, if x goes from 0 to y, if x goes from 0 to y, x will always be less than y. If x is in between 0 and y. Oh, x is less than y. Fair enough, it's also bigger than 0, but x is less than y. That's what we wanted. So that works like a charm. Let x go from 0 to y. Again, if you let x go between 0 and y, then x is less than y. And, why don't you go from negative infinity? Because they told us that x has to be bigger than 0. Okay. Now, never ever when it comes to integrals, worry about endpoints. Don't say, wait a minute, something's wrong here, because if x is in between 0 and y, and you do include the endpoints, then you have that x equals y. Don't worry about that. You never have to worry about whether you include endpoints or not. Just do the easiest way. Otherwise, we'd have to say y minus epsilon, and then take the limit as epsilon goes to 0. Okay? 0 positive. Okay, that is, you want epsilon to be positive. So, you don't want to add something there. If epsilon is negative, then you'll really be adding a small number. You want it to be a little bit less than y. You want x to be less than y. But you don't need to do this. You don't need to do this at all. Don't worry about the endpoints. Include it, don't include it, it's your call. Doesn't matter. Okay, so now this becomes integral 0 to infinity. In fact, the 2 comes way in front. And then I'll write the y pieces, e to the negative 2y, the y factors. And what's left is this, dx. So you have 2, the integral, 0 to infinity, e to the negative 2y. This integral is, we just did it, it's negative 1 over e to the x from 0 to y, which I'm going to call 1 over e to the x. I changed the sign from y to 0. dy is a typo right above. That should be dy. So we have 2 times the integral from 0 to infinity, e to the negative 2y. You plug 0 in, you get 1 minus, you plug y in, you get 1 over e to the y, dy. Come to the top. Let's do this. Okay, this is just Calc 2 stuff now. So this is equal to 2 times the integral from 0 to infinity. Distributing, I get e to the negative 2y minus, well, if you have e to the negative 2y over e to the y, you subtract the powers. Negative 2 minus, negative 2y minus y, negative 3y. Okay, e to the negative 3y dy. The first integral is e to the negative 2y over negative 2. I'll put the negative on top, minus. This integral is going to be e to the negative 3y divided by negative 3. That's going to make it positive. From 0 to infinity. Now, more formally in Calc 2, they told you to take limits, because as k goes to infinity, and integrate from 0 to k in proper integrals. Well, I'll be a little bit sloppy. But what I want to do first is put the e's in the bottom. From 0 to infinity. You put infinity here, you're gonna get a really, really large number. You double it, it's even larger. Divided by -1, it's 0. Zero plus. Same argument here. 3 times really, really large is really large. E to really large is even larger. 3 times that is super large. 1 over that is 0. Minus. Now you plug in 0. 2 times 0 is 0. E to the 0 is 1. 2 times 1 is 2. With the 1 on the top. Plus, same argument. This is going to be a third. This is going to be a third. Okay. Except the first one's going to be -1/2. -1/2. Okay, so what you get is 2 times negative. Well, this is +1/2. Why don't we do that? +1/2 minus 1/3. 1/2 minus 1/3. Working up, please. The common denominator will be 6. I multiply top and bottom by 3. I get 3 over 6. Minus. I multiply top and bottom by 2. I get 2 over 6. So I have 2 times, or 6, which is 1/3. 2 goes into both of those numbers 1 and 3 times. 1/3. Okay. So the next one, we need to be able to do this. You have 2 random variables, continuous. What if you want to find the density of the random variable x divided by y? X divided by y. So first we're telling that we're being told that the joint density function of x and y is given by f of xy is equal to e to the negative x plus y, or 0. So e to the negative x plus y whenever x and y are in between 0 and infinity. And it's 0 otherwise. So now we want to find the density function. Find the density of the random variable x slash y, x over y, which is different than x given y. The little slant in that line, the division line. Okay. So, if a is bigger than 0, then f of x slash y of a is the probability that x over y is less than a. actually less than or equal. And this is the double integral of e to the negative x plus y dx dy over x over y is less than a. But that means that x is less than a times y. A is less than a times y. E to the negative x plus y dx dy. So the outer integral, its limit should be y. And y goes from 0 to infinity. But now what does x go from? Now we know that x must be less than or equal to ay. And we also know that x is bigger than 0. So that's it. X goes from here to there. X goes from 0 to ay. And we just integrate this. Integral from 0 to infinity. The integral of this is, well, the integral of e to any power is e to that power, divided by the derivative of that power with respect to x. The derivative of negative x is negative 1, minus the derivative of y is 0. Dividing by negative 1 is the same as multiplying by negative 1. And we go from 0 to ay. And then that gets integrated with respect to y. So we have the integral from 0 to infinity. And remember, that's an x there. That is, these limits go in for x. So I get e to the negative ay plus y. And, okay, actually, I'm going to switch the limits to get rid of that minus. Somehow I didn't write down that minus. So first I plug in 0 for x, and 0 plus y is y, minus y. Minus, now I plug in the other limit, and I get e to the negative ay plus y dy. And the first integral is negative e to the negative y, and minus, and the second integral is e to the negative ay plus y, divided by the derivative, which is negative a minus 1, or negative a plus 1. And this goes from 0 to infinity. Erase the top, do the substitution, and we'll be done with this problem, and we'll be done with this section. It's a heavy-duty section, folks. You have to know all your definitions. All right. This negative over negative is going to become positive. So I have negative 1 over e to the y plus 1 over a plus 1 times e to the ay plus y. And this goes from 0 to infinity. When you plug infinity, this will be 0, and so will that one. So you get 0. Minus. Now you plug in 0. E to the 0 is 0, so is 1. E to the 0 is 1. So you get negative 1 over 1 plus. You have 1 on top. You have a plus 1. And now you plug in 0. You get 0 as a power. E to the 0 is 1. Times n by 1 doesn't do anything. The 0 doesn't matter. This is negative 1. You take away negative 1, you get 1. Minus that. Minus 1 over a plus 1. This answer is fine, or you can get a common denominator. 1 is a plus 1 over a plus 1. Minus, and this is clearly 1 over a plus 1. The numerator is a, the bottom is a plus 1. Okay, that completes this section. Jointly distributed random variables.